we talked about how Liouville's theorem implies that the only things that are conformally diffeomorphic to the solid unit ball in dimensions 3 and above is just the half plane or the ball itself or a ball itself. Things conformal diff to solid unit ball, balls, and half planes or half spaces. Okay. Which is dramatically smaller class than what we know is true in 2 dimensions. And this gives a hint of the fact that in higher dimensions, quasi-regular mappings are more restrictive. And one of the examples of that was this theorem I stated, that if you have a locally homeomorphic quasi-regular mapping, so if f from the entire Rn into Rn is locally homeo, is locally a homeomorphism, then globally a homomorphism which is false in 2 dimensions, even with conformal mappings. So note. False in R2, and the counterexample is just, or a counterexample is just given by this, e to the z. So this is one instance of this. Another version of this is the following. It's kind of a local version. So yes, I forgot to write that. If otherwise it's done before. Is quasi-regular. That would be a very strong theorem without that, right? Yeah. Cool. I should probably say K quasi-regular. I'll do that in the next thing. Okay, so next theorem. There exists a constant. Throwing all these unnecessary lines. C0, let's just call it C, which depends on K and N only, such that, and let's say this is belonging to 0, 1, such that if f from the unit ball, and this has got dimension n is bigger than or equal to 3, n is bigger than or equal to 3. If we have a quasi-regular mapping from the solid unit ball, f is k quasi-regular, let me make sure I have all the hypotheses here. Yep. And is locally a homeomorphism. then F on this smaller ball of radius C, K, N of 0 is injective. So this is kind of the most natural local version of the theorem above. The theorem above, we have the entire domain, and if we are locally a homeomorphism, when we have a quasi-regular mapping, then we're actually globally a homeomorphism, right? So you can deduce this from this theorem by simply taking rescalings and taking larger and larger balls, right? But what this says is that if we have a quasi-regular mapping defined in a ball, okay, and it is locally invertible, then there exists some constant such that for the ball of this radius of this constant C, which just depends on the K of the K quasi-regular and on the dimension N, we are actually injective on this central subball right here. Okay. So, well, yeah, you can just rescale this. So it's just a convenience to formulate this theorem around a ball of radius 0. But if you have a quasi-regular mapping, yep, you can just subtract the constant and then rescale to bring it to a ball of size 1. So if you have this hypothesis that you are quasi-regular on the entire Rn and you are locally a homeomorphism, then simply take balls of larger and larger radius centered on 0. Then by this theorem on a subball of radius C, K, N, R, where R is the ball you've taken, we are locally injective, and then R goes to infinity, and then we have injectivity everywhere. Because you can always do this kind of rescaling for functions. And so you can say, let's let F, we call it F of lambda of x equal F of lambda of x over lambda, right? And then if you take the derivative, then it's just, right? So this rescaling will preserve any properties of the derivative, right? So if you have a ball, if you have a domain, whatever, a huge domain and a huge ball inside it, just take lambda to be some number, whatever, 1 over the radius of the ball you have, if it's centered on 0, and then you'll have a quasi-regular mapping on the unit ball. Yeah, so being locally a homeomorphism doesn't mean very much. It means that for every single point, you have some small neighborhood where it's invertible. This is saying that actually you have some serious size sub-ball inside any ball for which it's locally invertible everywhere, for which that's actually true. On a sizable scale, yeah. It's a very strong theorem, and yeah, I'm just trying to think of the counterexample. Yeah, I'm sure this is not true in dimensions 2, and I'm just trying to think if there's an obvious way to change this to show that that's not true. Okay, I'll think more about that, but I'm absolutely sure this theorem is false in 2 dimensions with easy counterexamples. Okay, cool. So these are a couple of the main theorems about quasi-regular mappings in dimensions n and above. The other main theorem, well, there's several other main theorems. There's theorems about the way sets, the size of sets are changed. This involves telling you things about Hausdorff dimension and describing size of sets in various ways. But there are theorems about if you have a set of a certain dimension in the image, in the reference domain, what is the size in the image? And there are sharp controls on this. And these are very deep and important terms with many consequences, but we're not going to go into them. But we're going to talk about a theorem that we have mentioned, or at least mentioned in passing before. And Reshetnyak's generalization of Liouville's theorem. So Reshetnyak was the guy who I stated before, who is principally responsible for the main theorem about quasi-regular mappings. So this was the one which was proved in the 60s or 70s that if F is quasi-regular, then, and this is dimension 3 and above, then F is open and discrete. So we know this in dimension 2, as I've talked about from the story of decomposition. There's no obvious analog of the story of decomposition in higher dimensions, and this is proved by different methods. But this is nevertheless a true theorem. And the same guy who proved this, and let me try and spell his name, was very interested for a long time to generalize Liouville's theorem. And he has a book whose main theorem is this, or at least one of the main theorems. So this is his theorem. So suppose, I think he states it on a ball, he does. Suppose F from the unit ball. So I'm gonna, if the ball is centered on 0, I'm gonna just drop the 0. So if you see a ball with a subscript, it means it's always centered on 0, okay? Which is a fairly standard notation. So we have F, and it is 1 plus epsilon quasi-regular, and F is 1 plus epsilon quasi-regular. Then there exists conformal map, which as we know is just higher dimensional Mobius mapping, such that the supremum distance between the inverse of this guy, of the conformal map phi, composed with F, minus just the identity mapping in the L infinity norm over the ball, is less than this constant delta of epsilon of n, where delta of epsilon of n, so this is bad way of doing the board, so where delta epsilon of n is such that the limit as epsilon tends to 0, delta epsilon of n goes to 0 as epsilon goes to 0. Okay. So what does this say? Let me try and connect these things like this. What does this say? So it says that that we are getting closer and closer to a mapping whose gradient is inside the conformal matrices. In fact, I'm going to show you it's just like an L infinity distance away from the conformal matrices, this hypothesis. And then if that's true, then we can find some quasi-regular mapping that for which this is the case, which is morally saying that the L infinity distance between F and this guy is small, but small of order delta of epsilon, where delta of epsilon is not anything we know about, except that as epsilon goes to 0, delta goes to 0. So we have no quantitative control. We just have that as epsilon goes to 0, this goes to 0. Yeah? Okay, so I'm going to erase the board, and then we're going to talk about this theorem and its hypotheses. Everybody clear before I erase? Okay, so So the hypothesis was that f is 1 plus epsilon quasi-regular. Right? So what does that mean? That means that if we take the derivative of f at some point to the nth power, this is controlled by 1 plus epsilon, the determinant of the gradient. Right? So let's just fix, so this is true for almost every x. So almost every x. So fix assumption x, so fix x. And let's think about what this is saying. So implicit in this is that the determinant is non-zero. Start again, is non-negative. It might be 0. No? And so we can just take polar decomposition of this matrix. So take polar decomposition of this matrix. And I'm going to not write the dependence on x because x is fixed. So it's going to be some rotation matrix R and then some symmetric matrix S. R is rotation, and then S is in the symmetric 2 by 2, and it's positive definite symmetric. So all the eigenvalues are actually non-negative. Okay, so this is polar decomposition. This is linear algebra. So S being symmetric and positive definite, F is a diagonal matrix after some change of variables. So there exists some rotation matrix. Let's call it O. So we can write O. Let's write it the other way around. We can write that for some rotation matrix O, we can do this, that this symmetric matrix is a diagonal matrix with, say, entries A1, A2 up to AN, like this. And these AI are the eigenvalues of this symmetric matrix. AK eigenvalues. Of S, right? So let's, in terms of this stuff, see what that says for our eigenvalues A1 up to AN. Well, the operator norm is the largest eigenvalue, right? Because the operator norm is the thing that will do the maximum stretch. Let me write that down. So is equal to the supremum absolute value df of x acting on any unit vector v, where v belongs to Sn minus 1, right? And after we look at all of this stuff, then what is df? It's a rotation times S. S is a rotation times diagonal matrix times another rotation, right? So if you unwrap all of that, what we have is a rotation, a diagonal matrix, and another rotation. Yeah? And then the thing that's going to stretch things the most is the thing that's going to hit the largest eigenvalue. Is that clear to you? Okay. Everybody happy with that? Yeah, thumbs up if so. Cool. So then this thing is equal to just the max. So these guys are all positive, so I think the absolute value, let's do max of A1, A2, say up to AN. And let me rearrange my notes. So this is the max of all of these guys, and let's give that guy a name. Let's call it AK0, right? So one of these guys is the max. Let's call it K0, yeah? And well, actually, just let's call it A. Let's call it AK. Let's try and remember the K is fixed. All right, so this is what we know about the sup norm. So what do we have from this thing right here? Let's call this thing star. So from star, we have that ak to the n is less than 1 plus epsilon. And then this guy here is the determinant of this guy. But again, this guy is just a rotation times this diagonal matrix times another rotation. So the determinant is just the determinant of the diagonal matrix, which is just the product of the entries. Yeah? So that's A1, A2, all the way up to AN. Yeah? Cool. And AK, remember, was the biggest eigenvalue, right? So let's extract the smallest eigenvalue as well, right? So let's extract the smallest eigenvalue. So that's less than 1 plus epsilon, and then the minimum of all of these guys. So there is the minimum inside this list, 1, 2 up to n, certainly belongs there. And all the other guys, they are bounded above by this guy, which is the maximum. So we're going to put here ak to the n minus 1, like that. Yeah? So then dividing through by ak to the n minus 1 epsilon, then this implies that ak over 1 plus epsilon is bigger than or equal to the minimum eigenvalue, like this, right? And note that 1 over 1 plus epsilon, that's the same as 1 minus epsilon plus epsilon over 1 plus epsilon. And that is the same as 1 minus epsilon over 1 plus epsilon. We're going to assume epsilon is less than 2, so then this thing is bigger than 1 minus 2 epsilon. Yeah, not 2 epsilon. Which way around am I going? Yeah, bigger than 2 epsilon. I wrote epsilon over 2. Okay, so then this thing, let's write it like this. 1 minus 2 epsilon ak, the maximum eigenvalue, is bigger or equal to this thing here, right? So this implies that, in fact, all of the eigenvalues are pretty close to each other in value. So 1 minus 2 epsilon ak is bigger than any of the eigenvalues. Let's call them ai, which of course is less than ak itself. Yeah. So what does that mean? That means that the distance between this diagonal matrix A1 up to AN minus just the identity times AK is less than 2 epsilon AK, maybe with an n here, 2n epsilon AK, because there are n of these guys. Yeah? Cool. So what does that mean for our situation? Well, that means, again, since this thing, the gradient of df, let me actually just finally write it down instead of keep saying it. It's equal to some rotation, then this diagonal matrix, and then another rotation, R2, R1, R2, our rotations, dimension n. Yeah. So from that, from this and from that, it's clear that the distance of the gradient away from just conformal matrices is less than 2n epsilon, then the highest eigenvalue, yeah? And the highest eigenvalue, again, is the operator norm, like this. Like this. Yeah? And that's true for every single, for every x for which this gradient is defined. Yeah? So this is an L infinity type control on the gradient. Yeah? This is an L infinity type control on the gradient. And in fact, if, so let A of x belonging to the conformal matrices be such that the distance of the f of x conformal matrices is like this, then what is that going to say? Well, then if we do the following thing, so this is less than 2n epsilon gradient of f, like this. Okay, and again, epsilon is small, so this also means that, for example, the gradient of f in the supremum norm is bounded by, for example, 2 times the operator norm of the gradient of A. Just because I can take the triangle inequality and so that's less than 2n epsilon, the operator norm of A of x, like this. Yeah. So just looking at this inequality right here, let us compose on the left-hand side with a to the minus 1. And let's change this thing. This is now the Hilbert-Smith norm. Let's change it to the operator norm. And these are all in the space of finite dimensional matrices, n by n matrices. So all these norms are equivalent up to some constant. So we're going to lose some constant, but we don't care too much. Go ahead, Josh. This one? Yeah, okay, I did that a little bit fast. Let's put it here. So we have this guy, right? So from this inequality, we have that minus A of x plus the f of x is going to be less than, let's put it here, 2 epsilon n epsilon this, the f of x, like this. Just from this that we know, yeah? Even operator norm, not that makes a difference. So let's is bigger than equal to, is equal to the f of x minus 2 epsilon n the f of x, like this. And then again, since operator norms are all equivalent, since norms in finite dimensional space are all equivalent, then this thing is bigger than, say, 1 over 2, the norm like this, right? Yeah. So there is some, now there'll be some constant because there's some constant we got from this, but yeah, so let's put 4 here instead of 2, but that should be enough. Yeah. Cool, thank you. All right, so let's rewrite this for the operator norm, first of all, and then let's compose with a to the minus 1 on the left-hand side. So we have that the f of x, let's put it on this side. So a of x to the minus 1, the f of x minus a of x, like this. This thing, okay, is less than the operator norm of a to the minus 1 of x, and then this thing, the f of x minus a of x, operator norm. Operator norm by some constant is bounded by Hilbert-Smith norm, And so then this is less than some constant. Now I'm just putting constants of operator norm to -1, oops, of x, and then there's an epsilon here, so constant times epsilon operator norm times the operator norm of a of x, like this. But A is a conformal matrix, right? So the operator norm is the same as the determinant to the root power, right? So this is equal to constant times epsilon, the determinant of a to the -1 of x to the nth power, right? And then determinant of a of x to the nth power, like this. And the determinant of a to the -1 is 1 over the determinant of a, right? So then this thing overall is just less than equal to constant times epsilon. Yeah? And then continuing this thing through, and then let's replace the operator norm by the Hilbert-Smith norm, and then we have that a to the -1 of x, the f of x, minus the identity is less than this. So as a result of all of this, what does this hypothesis say? This hypothesis says that for every x for which the gradient of f exists, there exists some conformal matrix such that if we compose on the left-hand side with the conformal matrix times the gradient, then that thing minus the identity is less than constant times epsilon. Yeah? And that's the correct scaling for the conclusion of the theorem, because what's the conclusion of the theorem? The conclusion of the theorem is that there exists conformal phi such that phi to the -1 composed with f minus the identity in the L-infinity norm around the P1 is less than delta epsilon n, right? Yeah? No, no, that's the theorem. That's the big theorem. So what is this? This is a pointwise condition, right? This is that for every x, there exists some conformal matrix, yeah? And then this thing, as you say, it's not about the gradient, it's about the function itself, yeah? But if it was about the gradient, it would say that the gradient of this guy composed with the gradient of this guy is close to the identity matrix, yeah? But the point is that this is independent of this is the way to formulate the hypothesis that is independent of the actual function itself, right? So if I stated it like this, then it's a little bit obscure what this means because it depends on the function itself, and it seems a bit strange. Yeah, so this is just a reformulation of the hypothesis. This is just a reformulation of the hypothesis. Okay, yeah, I probably should have written that somewhere before I did all this stuff. Yeah. Thank you for this question. Is it making sense to other people now? Thumbs up if so. Thumbs down if not. Or speak up if not. Okay, cool. So, yeah, the moral is exactly as Josh was saying, that we have hypothesis on the gradient and we conclude something in terms of the function, not the gradient. And we control something which is much weaker. So we lose any, this is the, epsilon is in the hypothesis, and in the conclusion we have delta of epsilon. And delta is going down to 0 with epsilon, but it could be massively bigger, right? We have no control on the actual rate. Yeah? Cool. But that was, that was a big theorem in its day, and a lot of work went into this, and the proof is not trivial at all. This is very hard work to prove this. Yeah? That's right. In this form of the theorem, there's no quantitative estimate for delta. What I'm about to show you is that if you have a stronger hypothesis, you can get quantitative control But at the moment, there is no, for the full theorem where you insist that the hypotheses are that the gradient is in some sense close to conformal matrices, the full set of conformal matrices, there is no quantitative control of this delta of epsilon. So contrast that with Muller's theorem, where the hypotheses were that the distance of the gradient away from rotations was of order epsilon, and the conclusion was that the distance of the gradient is away from, the distance of the gradient away from rotations is of order epsilon, and the conclusion is that the distance of the gradient away from a fixed rotation is of order epsilon as well, right? So epsilon in for the hypothesis, epsilon out for the conclusion. Here, epsilon in for the hypothesis, delta of epsilon out for the conclusion. The conclusion is only about the function, not the gradient, and delta of epsilon is in no way controllable, understandable in terms of epsilon. So we're going to compare this to one of the theorems that I suggested, or I put in the list of things to potentially read, and that's the, we talked about this before, the Muller-Sverak-Yan theorem, which said the following, that if we have a sequence, so we have UK belong to W1 n over 2, omega into Rn, and we have that UK are weakly tending in W1 n over 2 to some limiting function u, which means the gradients are converging weakly in L n over 2, and the functions are converging strongly, but the important part is the gradients are converging weakly. And we have that the integral of the distance to the power n over 2 of the gradient away from conformal matrices is tending to 0, then this implies that the gradient is actually converging strongly in LQ to this limiting function for Q, which is between 1 and strictly less than n over 2. So that's the theorem, and this is actually providing a kind of version of Reshetnyak's theorem in itself, because so this is my claim. So claim, there exists from this exists some delta epsilon n, delta with the limit as epsilon goes to 0, delta epsilon n going to 0, such that if this is true, that the distance of nth minus 1 du away from the conformal matrices is equal to epsilon, then this implies that there exists conformal phi such that the integral of omega of the distance to the slightly lower power q, sorry, stupid way to write it like this, that the gradient away from gradient of phi to the q dx is less than delta of epsilon of n, like this, or some constant like this. Well, actually, we don't need a constant, we can incorporate in this. All right, so this is analogous hypotheses, except we don't have a pointwise control, which we had in the hypothesis of Reshetnyak theorem. This is a LP control, so some of these gradients are allowed to be far away from these conformal matrices, and the conclusion is about the gradient itself. Okay, so tell me why from this we can conclude this. Tell me why, and then we're done for the day. well, suppose it's false. So for some, say, delta bigger than 0, there exists sequence of functions uk belong to W n over 2 omega into Rn, such that this is true like this. Oops, it's tending down towards 0. Yeah. Okay, it looks like I need an extra hypothesis. Okay, I'm going to add a hypothesis such that this is true and the L over 2, n over 2 norm of this is less than A, then this. So I've just realized I don't have the right to take a subsequence. So A can be any big number. Okay. So if this is true, we have a sequence of this, and this gradient is less than A. So as we've seen before, if we have a bounded sequence in LP, then we have a weakly converging subsequence. So take weakly converging subsequence. Let's call it UKN. So in other words, the gradients of UKN will converge to weakly in n over 2 to the gradients of this guy for some u belonging to W n over 2 omega Rn. So by this hypothesis, oops, this should have been the K. Since the gradients are closer and closer to this set of matrices, this is also going to be true of the weak limit. And that's not completely trivial, but it is nevertheless true. Okay, so this implies that the U belongs to the conformal matrices almost everywhere. And it's sufficiently regular, so this is a big theorem, that this is sufficient regularity. So actually, U is Mobius. It is one of these guys. It is given by M times a reflection times this let's call the reflection. Let's call the reflection Q times A times this reflection I, and then just x minus A over mod x minus A squared plus some constant B. Right? So it is a Mobius mapping. Yeah? But the gradients are converging strongly. If you accept this, I agree it's not true, but if you accept this is true, then what are we in position to conclude? So we have a weakly converging subsequence like this. We have that gradients converge strongly because applying this theorem, we have that the gradients converge strongly to this thing. Yeah. So therefore, the conclusion is that the U gradient n minus the gradient of U, which now is this Mobius thing, right, to the power q dx is going down to 0 as n goes to infinity, like this, right? Because that is the conclusion of the Muller-Sverak-Yan theorem. Yeah. But that contradicts hypotheses that oh, I didn't even write this down, that for some delta it's false. So suppose it's false for some delta. In other words, the distance of the gradient away from the conformal matrices is always away from any Mobius mapping is always bigger than delta. Then that would be false, because we can get this to be as close to 0 as we like for some subsequence. Yeah. So yeah. So with this additional hypothesis that we insist that there's a bound on the actual norm of the gradient in n over 2 and LP n over and L n over 2, then we get a theorem that is a bit stronger, because we control the hypotheses and we get control similar kind of loss of, we don't know the constant here, but we do know control of the gradient. Right? Instead of just controlling the function, we control the gradient, which is a much stronger thing. Okay, so good point about this. Yeah, that's the moral, that a non-quantitative estimate isn't much stronger than a compactness theorem that sends you towards the set of objects that you should be approximating. So yeah, that's the moral. I'm out of time, but I also wanted to say again this theorem about, I mean, I'll summarize this, I guess, on Friday, that that was proved by Farako and Zhang, that if you take a subset of the conformal matrices that excludes 0 and that is bounded as a compact subset, then there's actually a quantitative control that if you are pth distance away from this subset in terms of epsilon, so the LP norm of the distance of the gradient away from this subset is equal to epsilon, say, then actually there exists a single Mobius mapping such that the gradient away from this Mobius mapping is of order constant times epsilon away. So that is full quantitative control. In that case, the delta is equal to the epsilon. And that's an even stronger theorem, but that requires that we take a subset of the conformal matrices that excludes 0 and is compact. Final word on this. This was using ideas, I mentioned briefly, of quasi-conformal mappings. Start again. Quasi-convex mappings, which are an idea from calculus of variations. And I'm not going to write it down because I'm over time, but I'll write it down next time. So I'm going to show you some applications of quasi-conformal analysis to calculus of variations, but there's been a kind of cross-fertilization that ideas from calculus of variations have also improved stronger versions of classical theorems of quasi-conformal analysis. All right, that's it for today. Any final questions before, oh, wow, way over time, before we sign off? All right, so see you all on Friday.